Welcome back. We've got a lot to cover in this section. Some of it we've already touched upon in a previous section, but for the most part, this is easy material. We're going to talk about circulation, temperature inversion, dew point, humidity, the different cloud types, and also the beginning part of thunderstorms. The atmosphere is in constant motion due to the uneven heating of the Earth's surface. As the temperatures increase, the molecules spread apart, becoming lighter and rise, and the opposite is true as the temperature decreases. This creates airflow. Atmospheric circulation. This is caused when an air mass is passing over warmer surfaces. Creates convective currents, causing the air to rise. This creates an unstable air mass with good visibility because the air is moving around. Add some moisture, the unstable air creates cumulus clouds. Here's an example from the pilot handbook. Here we can see a sea breeze coming into the landmass, warmed up by the landmass and rising, and then eventually moving back out towards the body of water. The process is reversed at night. Let's take a look at the opposite, an air mass passing over a colder surface. This creates a stable air mass with poor visibility. That's because there's no circulation. The smoke and dust and other particles are trapped towards the surface. In this example, it may produce stable air mass that can produce low stratus clouds. We'll talk about that in a later slide. It may also produce fog, but it definitely resists vertical movement. No convective currents mean no circulation to clear the air. Next up, temperature inversion. We already know that the temperature of the atmosphere decreases as the altitude increases. So the opposite of that, temperature inversion, is when the temperature of the air increases with altitude. This creates shallow layers of smooth, stable air close to the ground. Air at the top of the layer acts as a lid. That's why stable air typically has poor visibility. If the relative humidity of the air during a temperature inversion is high, clouds, fog, haze, smoke may result in diminished visibility. That's because the lid that we previously talked about keeps the air from moving. Another type of temperature inversion is surface-based temperature inversion. This occurs on a clear, cool night when the air close to the ground is cooled by the lowering temperature of the ground. Condensation and saturation. Condensation is a phase transition by which vapor is changed into a liquid. Anytime there's a change between a gas to a liquid to a solid, and a solid to a liquid to a gas is called a phase transition. In this case, condensation may appear as clouds, fog, mist, dew, or frost. Now let's talk about saturation. This is the maximum possible quantity of water vapor that an air parcel can hold at any given temperature and pressure. Unsaturated air is an air parcel that can hold more water vapor. Okay, just one additional note for saturation. Saturation is a point at which a parcel of air can no longer hold any more water vapor. Once it goes over that point, then it becomes condensation. Awesome. Dew point. This is given in degrees, and this is the temperature at which the air can hold no more moisture. When the temperature of the air is reduced to the dew point, the air is completely saturated, and moisture begins to condense out of the air in the form of fog, dew, frost, clouds, rain, or snow. All right, next up, humidity. This is the amount of water vapor present in the atmosphere. Relative humidity is the actual amount of moisture in the air compared to the total amount of moisture the air could hold at that temperature. In other words, based on the temperature, that parcel of air can hold only so much moisture. So it is relative depending on the temperature. Dew is moisture that has condensed as a result of reaching the dew point. Dew poses no threat to manned aircraft. However, that may not be the case for all models of drones and SUAS. Those electronics may be susceptible to condensation on a small aircraft. However, frost is a definite flight hazard. This disrupts the flow of air over the aircraft and can drastically reduce the production of lift of the aircraft. It also increases drag. So how does frost develop? Well, we need moisture and we need freezing temperatures. Pretty easy, right? We've already talked about convective currents, but let's dive into it just a little bit deeper. We already know that convective currents are air movements that moves up or down, not horizontal like wind. At lower altitudes during warmer weather, convective currents cause bumpy, turbulent air. Convective currents may also be experienced near land masses directly adjacent to large bodies of water. All right, convective turbulence. Let's talk a little bit about convective current first. We usually think of convective current as air rising and then somewhere else it's descending. For convective turbulence, the rising and sinking are closer together. We may also see evidence of convective turbulence with billowy cumuliform clouds. A cloud top may mark the approximate upper limit of a convective current or convective turbulence. Larger towering cumulus clouds and cumulonimbus clouds sometimes have an anvil-like top. When you see cumulonimbus clouds, take it as a visual warning that violent convective turbulence is present. Let's talk about 4 basic cloud types. Cirrus clouds are above 20,000 feet, and nimbus clouds indicates rain every single time. Cumulus clouds are usually identified by the fluffy cotton ball nature of the cloud. Stratus means layer, and these type of clouds will cover large areas of the sky, sometimes the entire sky. Here's a great example of stratus clouds. If we look back at the METAR weather report or TAF weather forecast, how would this be reported? Most likely in those reports, this sky condition would be reported as broken, in other words, 5/8 to 7/8 cloud cover. We're going to focus mostly on the left-hand side here. Above 20,000 feet, we have the cirrus clouds. And between 20,000 feet and 6,500 feet, we have alto clouds. Below 6,500 feet, we may have stratus clouds, nimbus clouds, cumulus clouds. In this example, we have Castellanus clouds. This has a common base with separate vertical development. These are the beginnings of towering cumulus. Here's another example of the same cloud type, common base with separate vertical developments. Lenticular clouds are lens-shaped, just like the name suggests, and we can expect strong winds with these types of clouds. They are formed usually over mountains, but not always. Towering cumulus clouds. When we see this, we can definitely say there is instability in the atmosphere, particularly closer to the clouds and within the cloud. Towering cumulus clouds are a precursor to cumulonimbus clouds and/or thunderstorms. Cumulonimbus clouds hold large amounts of moisture and have unstable air. This weather phenomenon has many hazards, such as lightning, hail, may have tornadoes, definitely gusty winds, and wind shear. With regards to aviation, cumulus nimbus clouds are considered the most dangerous cloud type. Here's a thunderstorm with a few of its hazardous elements: a tornado, rain, and hail in the background. There might be some lightning in there as well. Take a look at the anvil and the convective currents and convective turbulence that is overshooting the top.